Hey guys, so what we're going to do today, we're going to review Hardy Weinberg Equilibrium. So I went ahead and graded your fishy frequencies lab, and most of y'all did pretty okay with Hardy Weinberg, but I did notice a couple of y'all were struggling with the same issues. So we're actually going to go over the 6 practice problems that were at the end of your fishy frequencies. So if you feel that you did great, you understand a Hardy Weinberg Equilibrium, you can go ahead and move on to the assignment that I have posted in Google Classroom. If you feel like you need a little bit of practice or you just want to review those problems, go ahead and stick around and I'll go ahead and go over all 6 of those problems. So what is Hardy Weinberg? So Hardy Weinberg is a set of equations that we can use to determine whether or not evolution is occurring in a population. So in order to determine this, we're going to be looking at the allelic frequency. So with our first formula is P plus Q equals 1. P represents our dominant allelic frequency, Q represents our recessive allelic frequency, and they both have to add up to 1, which would be 100% of the population. So because they have to add up to 1, we would need to get the percentage of our allelic frequencies and change them into a decimal. So our second formula is a little bit longer. It's P squared plus 2PQ plus Q squared equals 1. So P squared, just like P represented the dominant allele, P squared is for homozygous dominant individuals, so big A, big A. 2PQ represents our heterozygous individuals, big A, little a. And Q squared represents our homozygous recessive individuals, little a, little a. So if we take the percentages of all the individuals in a population, we would change that into a decimal, and it should ideally equal 1, or as close as possible. So how do we know that evolution is occurring? Well, if you remember your 5 fingers of evolution, those criteria would help us determine whether or not a population is capable to evolve. So for Hardy Weinberg Equilibrium, if we have a population in a completely ideal situation, then no selection would occur. No natural selection, no sexual selection, nothing like that. So you would not be selecting for best fitness at all. You also wouldn't have any mutations introduced into the population, absolutely no migrations, and your population would be as large as possible. The smaller your population is, the more likely it is to evolve. And then lastly, you would also have to have random mating. So if all 5 of these criteria are met, then the likelihood of evolution occurring is very, very little. And so if we use our 2 formulas, we would be able to calculate our frequencies before an event and then after an event. And if the numbers are similar, then we could determine that evolution has not occurred. All right, so our first problem that we're going to be looking at. In Drosophila, the allele for normal length wings is dominant over the allele for vestigial wings. If you remember from earlier in the year, vestigial wings are stubby little curls that cannot be used for flight. In a population of 1,000 individuals, 280 show the recessive phenotype. How many individuals would you expect to be homozygous dominant and heterozygous for this trait? What would be the total number of dominant and recessive alleles in the population? So this is asking for 2 things. It's asking for our genotypic frequencies, so homozygous dominant and heterozygous, and it's also asking for our allelic frequencies, so our dominant and recessive alleles. So what it does give us, it gives us that there's 1,000 individuals in the population. 280 show the recessive phenotype. So that means that 280 out of 1,000, which equals 0.28, are going to be homozygous recessive. So if they're homozygous recessive, and if we use our formula, we know that 0.28 is our Q squared. All right, so in order for them to be homozygous, they have to be, let's say, little a, 280 of them are little a, then that means that 0.28 is going to be our Q squared. This right here is for our homozygous recessive. Okay, we always have to start with our recessive population. So if we have Q squared, we can go ahead and figure out Q. So in order to get Q by itself, we're just going to square root this. So if we take the square root of 0.28, that should give us our Q. So Q should equal 0.53. Okay, and I did these calculations a couple of times. Let me know if I get something wrong. So 0.53 is going to be our Q. So now that we have Q squared and we have Q, we can use our formula P plus Q equals 1 to figure out what P is. So if I take 1 minus Q, okay, which is 0.53, I should be able to get my P value. Okay, so 1 minus Q equals P. So 1 minus 0.53 equals 0.47. Okay, so 0.47 is my P value. All right, so far I figured out my Q squared, I figured out Q, and I figured out P. So now I can use my second formula. So remember, I have P squared plus 2PQ plus Q squared equals 1. I've already done this one. Okay, so that one's good. That one was 0.28. I couldn't just use what was left in the population to figure out my dominance because I don't know if it's homozygous dominant or heterozygous. So now I'm going to use my Q and my P. So P squared, I just take my 0.47 and square it. Okay, so when I do that, I should get 0.22. Okay, so that's my P squared. 2PQ, I'm going to do the same thing. So 2 times 0.53 times 0.47. Okay, and when I do that, I end up with 0.50. So I did have to round a little bit when I did this, and so if you add it up, it's not going to add up equally to 1. It's going to be close, but it's not going to be entirely close. It's not going to be entirely exactly 1. So if I look back up here at my problem, it asks how many individuals would you expect to be homozygous dominant and heterozygous for this trait. So some of y'all just left it at the frequencies. So it asks for number of individuals. I have 1,000 individuals in my population. So what I need to do is I need to take these frequencies and multiply it by 1,000. So for my homozygous dominant, which is right here, okay, so this was my homozygous dominant. Okay, I know that there is 1,000 individuals in the population. So I'm just going to take this number and multiply it by 1,000. Okay, so for number of homozygous dominant, okay, sorry for my handwriting. Okay, so I'm going to take 0.22 times 1,000. So I should get 220 individuals that are homozygous dominant according to my equation. So on the opposite of that, I need to also do my heterozygous, so 0.5. So same thing, number of heterozygous. Okay, so I have 0.5 times 1,000. Okay, and I'm going to get 500 heterozygous individuals. Okay, so that was one part of the problem. The second part of the problem is asking for my alleles. Okay, so it's asking what are my total number of dominant and recessive alleles in the population. So some of y'all got a little bit confused on this. I think I only had 2 people that actually got it, which is awesome for you guys. So if you think about the alleles that an individual has, so your alleles, remember, those are the genes that are on your chromosomes. So if you have a set of chromosomes, okay, there's one. Okay, there's another. Okay. If you remember your chromosomes, okay, here's your alleles. Okay, alleles are your locations of your genes. So let's say that you got big A from mom and little a from dad. So everybody, because they have genes from both their dad and their mom, they're going to have 2 sets of alleles. So if you have 1,000 individuals in the population, the total number of alleles in the population equals 2,000 because everybody has 2 alleles. So I already know my p-value. Okay, so P we said was 0.47, and we said Q was, let's see here, 0.53. All right, so if I have these numbers, I can't just multiply them by 1,000. I have to multiply them by 2,000. So P, okay, so for my number of P alleles, okay, number of dominant alleles, I'm going to do 0.47 times 2,000. Okay, so let's see here. I should have 940 dominant alleles. Okay, 940 dominant alleles. So on the opposite of that, 0.53 times 2,000. Okay, so from there, I should have 1,060 recessive alleles. All right, so that's the answer for number 1. So hopefully y'all got that. Okay, if you got that, you can go ahead and move on to your next set of problems. Okay, so if not, stick around. We're going to go over the next problems. All right. And I apologize for my little document camera. I had to make do with what I have here at home. All right, so for number 2, the allele for unattached earlobes is dominant over the allele for attached earlobes. In a population of 500 individuals, okay, so now I have 500, 32% show the recessive phenotype. How many individuals would you expect to be homozygous dominant and heterozygous for this trait? What would be the total number of dominant and recessive alleles in this population? So this is pretty much the same as number 1. The only exception is that there's 500 individuals and it gives you a percent for your recessive phenotype. So that's actually kind of nice. If it gives you a percent, we just change that into a decimal. So we have 0.32 for our homozygous recessive. Okay, and if you remember, homozygous recessive is our Q squared. So if we have Q squared, we just need to take the square root of that to figure out Q. Okay, so Q from here is going to equal 0.57. So next, P plus Q equals 1. So we're going to do 1 minus Q, and we'll be able to figure out what our P value is right here. So 1 minus 0.57, and that's going to equal 0.43, which is our P value. Okay, so now we have Q, now we have P. So if we look at our problem, it asks how many individuals are homozygous dominant and heterozygous, and what would be the total number of dominant and recessive alleles. All right, so in order to figure out the first part, we're going to use our long formula. P squared plus 2PQ plus Q squared equals 1. So P squared, 0.43 squared. Okay, so our P squared is going to be 0.18. 2PQ for our heterozygotes, 2 times 0.43 times 0.57. Okay, so that's going to equal 0.49. So it didn't ask for our frequencies. It asked for the number of individuals. We have 500 individuals total. So we'll be able to calculate how many are each of these genotypes by taking our number and multiplying it by 500. So our number of homozygous dominant, okay, P squared, we're going to take 0.18 times 500. So what we end up with is we end up with 90 that are homozygous dominant, okay? Okay, on the opposite of that, number of heterozygous. Okay, heterozygous is 2PQ. We're going to take our number 0.49 and multiply it by 500. So when we do that, we get 245 that are heterozygous. Okay, so that's the first part of our problem. The second part of our problem asks for the number of alleles. So we have up here Q, we have P, but it asks for alleles. And if you remember, I told you that each individual has 2 alleles. You got one from mom and one from dad. So even though we have 500 individuals in the population, we have a total of 1,000 alleles. So for our Q frequency, we have 0.57. So if we multiply 0.57 times 1,000, okay, this equals the number of recessive alleles. Okay, so let's see here. That should be 570 recessive alleles. On the opposite of that, 0.43 times 1,000. This is our number of dominant alleles. Okay, so that should be 430. Okay, so this is the second part of that problem. Okay, so questions 3, 4, and I believe 5 are all asking the same types of questions. They're just using different numbers. So if you have any questions about those, definitely let me know. So one of the things I did want to go over problem number 6. So problem number 6 is a little bit different. So problem number 6, okay? In certain populations, the dominant phenotype of a certain trait occurs 79% of the time. What is the frequency of the dominant allele? So I can't start with a dominant phenotype. I can't start with that. I could start if they told me the dominant allele, but I can't start with a dominant phenotype because I don't know if they're homozygous dominant or heterozygous. So all I know is that that dominant phenotype, my physical trait, occurs 79% of the time. That means that my recessive trait is the rest of the time. So if my population is 100%, I can subtract 79% to get my recessive percent. So if I do that, so 100 minus 79, and apparently I lost my calculator. So 100 minus 79 should get 21%. Okay, so 21% is my recessive percentage. So that means that this is the number or the percent of homozygous individuals. Okay, so from here, I can change this percentage into a decimal. So that means that 0.21 is going to be my Q squared because 21% was my homozygous recessive individuals. So just change it into a decimal. 0.21 equals Q squared. And so from here, I can do what we've been doing all along. I'm going to take the square root of 0.21, so that way I get Q. Okay, Q by itself is 0.46. Remember, I used my formula, P plus Q equals 1. So using that formula, P is going to equal 0.54. And if I look at my problem, it asks, what is the frequency of the dominant allele? Well, dominant allele is P. So I'm already done. I figured out what my frequency of the dominant allele is. So out of my population, 0.54 or 54% of the alleles in that population are going to be dominant. All right. So if you have any questions about any of these other problems, or as you're doing the practice assignment, you find that you get stuck, definitely let me know and I'll try to help you out. All right. So until next time, bye.